Have you been able to grade the midterms yet?
Yeah. So I plan to start, or I had planned to get some other stuff done yesterday, but I got my vaccine yesterday morning, and it kind of laid me off for the rest of the day. So I'm a day behind, but I plan on getting started first thing tomorrow on it. So you guys should have it back by Wednesday.
Cool, thanks.
Mhm.
Were you talking about the exam?
Yeah, yeah. So I haven't started looking at them yet, but I'll probably start first thing tomorrow morning.
Okay. Oh, and a quick question. I'm writing out my report for 410 activity 2. So
Yep,
the idea is to like write it as if nobody knows what FEA is, just so they could understand it.
correct. Yeah.
But I guess okay.
have not. What is that? Oh, cool. I played Borderlands before. At least 1 and 2. Yeah, it's an experience. Yeah, it kind of is. Yeah. For some reason, the line I forgot exactly what the DLC is called, but it's like something about like Thunderdome, and they have like that ridiculous guy kind of yelling things at you the whole time, and like, and for some reason the line that always sticks out to me, it says, "There's nothing more badass than treating a woman with respect." Yes, yes, yes. Yeah, my friends and I, we had a lot of fun playing Border, because I think it came out when my friends and I were in college, and so that was kind of one of our go-to games while we were in college. That's cool. Hello? Hello? Can you hear me? Okay, great. All right, perfect timing. So it's 5:30. So let's go ahead and get started today. Good evening, everyone. How's everyone doing today? Doing good, I hope. Yeah. I'm ready for the break too. Yeah. Oh yeah. So speaking of midterms, I haven't had a chance to take a look at them yet. I was telling people before the class that I had planned to do it today, but there was some other stuff I was supposed to do yesterday. But then I got my vaccine yesterday, and it kind of made me tired for the whole day. So I ended up doing nothing. And so I'm start grading your midterms first thing tomorrow. And also, yeah, there was also daylight savings, which also didn't help at all. And so I'm a little bit behind, but by Wednesday you guys should I'll definitely have it graded by then, and we can talk about it on Wednesday. Yeah, not another week, just a couple days. Okay, and so another announcement I want to make is that homework 4 is posted, and so homework 4 was posted today. Is going to be due next Friday, and so we only have 2 more weeks of class before spring break. So we have this week and next week, and so I made homework 4 due basically right before the break, and so that you don't there's nothing for you guys to work on over the break. Probably I'll give you guys your the final projects before the break. If not Wednesday, then Monday for sure, and so you can work on that. But I wanted to make sure to not assign any homework over the break, but I'll do grading over the break, for that. Okay. And so homework 4, check it out. After Wednesday's lecture, you should be able to do everything on the homework, and after today, you should be able to do a lot of it as well. Okay. All right. So I think that's it. So I think the plan for today is we're going to continue on with time marching schemes, and so I think we left off last Monday, right before we were going to take a look at a MATLAB implementation. And so I posted that MATLAB code on Canvas right now, and so it's totally worked out, and so there's nothing for you to implement. But my plan today is to just do a little bit of a refresher at the beginning, and then go through that example, and then kind of move on to the part 2 of our time marching scheme, which is actual time dependent problems. right, question. So when will we talk about the project? And so I'm hoping, what I'm hoping is that I can grade your midterms by tomorrow and then type up the specs. I already have an idea of what I want you guys to do for the final project, but I haven't formally tested it and written up the specs yet. And so probably most likely, I think we'll probably talk about it on Monday of next week. Because I want to make sure I get the midterms graded for sure before Wednesday. Yeah. All right. Any other questions before we begin? I feel good. I mean, my left arm is sore, and yesterday I was pretty tired, but today I feel pretty much back to normal. Besides my arm being sore, but that's the only thing. So yeah, it was good. I went to the Fairplex in Pomona, and so it was nice. It was all drive through, so I never got out of my car throughout the whole process, which is kind of cool. Unfortunately, I can't. I don't have connections like that. Yeah, I got the Pfizer one. Can you get a hint on the final project? The final project is it's mostly going to be a big implementation of everything that you guys have been learning so far. And so we're just about done with I think the first half of the class, which is on finite difference methods. And so if you kind of notice up to this point, now that we're doing this, we're done with that whole equation. And so actually, after this week, you should be fully equipped to do the final project if you're an undergrad. So the final project will have basically, two options. So you can either do your final project with finite differences, which is, what we've been going over the last 8 weeks. But then for the second half of the class, we'll be going over a different method called finite volume. And so it's very similar. I mean, you end up kind of solving the same problems, just the way you get the equations is slightly different. And so if you're an undergrad taking this class and you're not taking for grad credit, you can either choose whether you want to do finite difference or finite volume. But if you're taking this for grad credit or you're a grad student, then you have to do both. And so you have to do both finite difference and finite volume. Final project is individual. So everyone's going to be doing writing their own code, and everyone's going to be writing their own reports in the end. There's no negotiation on that. Because everyone's going to be working on the same thing. And so, I want everyone to kind of work on that same code. Yeah, well, I'll have more details by Monday. It's not bad. You'll see. I it's going to be the same. I'll give you a big starter code, and you're going to have to just kind of fill it in from there. Yeah, I think you guys will be fine. I mean, you guys have been keeping up just well with the project. In theory, I mean, there's going to be small variations. I mean, everyone has their own coding style, of course, but the end solution should be the same for everyone. I will be doing Turnitin for the codes too. So I mean, you should write your own codes. Otherwise, Turnitin is going to flag it if you kind of copy exactly what someone else did. So, and you're going to have to write about it too. And so in the report, a big part of the report is I want you to basically explain, the methods of what you did and, everything that you did as well. And so, if you wrote your own code, then that method section should be very easy to write because you'll understand kind of everything that you did. So, so yes, in the end, everyone will be solving the same problem, but everyone still needs to write their own code. So yeah, so we'll talk about finite volumes later. It's not that bad. You'll see. Okay, and so so that's enough I want to say about the final project for now. I'll have a lot more details for you on Monday. Okay, but let's go ahead and kind of jump into the lecture for today. And today I want to talk a lot about how to implement time marching schemes for 2D problems. Okay, so I think last Monday or last time that we met up, we had just started talking about how to do unsteady 2D problems. So this is the end of lecture note 7, and so we're still kind of working on that one, and then we'll transition to lecture notes 8 sometime. All right, and so the full equation that we're solving for now is we have d phi dt plus u d phi dx plus v d phi dy is equal to k d squared phi dx squared plus d squared phi dy squared plus q of xy, right? So it's the whole shebang now. So, we have all of the terms that are included now. So we have unsteady terms, we have convection terms, we have diffusion terms, and we have the source terms, right? And so what we did from here is we took this differential equation, and just like we've always been doing for, for all these problems, is we replace all of the derivatives with finite difference. Okay. And we have an additional wrinkle here compared to what we did before, because now we have time that's a factor, right? And so, when we apply finite differences to our spatial derivatives, so things like our convection derivatives and diffusion derivatives, we have a choice of whether we can either apply either a time index of n or n plus 1, right? Okay. And depending on whether we evaluate them at n or n plus 1 will give us, our two methods, right? And so we're going to start with n because this is, a little bit of the simpler one. It's a little bit easier to implement. This leads to the explicit Euler method, right? But then if we assign everything at n plus 1, this leads to implicit Euler. Okay? So I'll leave implicit Euler, for the end of the class. Or for a later example, but for this example, just for kind of simplicity, I want to focus just on explicit Euler. Okay. All right. And so what this leads to is a lot of terms that are evaluated at phi n, and basically just one term that's evaluated at phi n plus 1. Right. And so we end up with the following. Before I do that, are there any questions on this? Okay. All right, and so if we do all that stuff, and so I'm not going to repeat the calculation because we did that last time, we end up with this kind of monster of an expression. So this is basically explicit Euler for 2D convection diffusion. Okay. And so we have phi I comma j at n plus 1. Okay. Remember, for our time marching schemes, we put everything at n plus 1 on the left-hand side and everything at phi n on the right. Okay. Okay. And so we have u delta t over 2 delta x plus k delta t over delta x squared times phi I minus 1 comma j at the evaluated n. Okay. And then we have the right neighbor term. So it's minus u delta t divided by 2 delta x plus k delta t over delta x squared phi I plus 1 comma j evaluated n. Okay. Plus v delta t divided by 2 delta x plus k delta t over delta y squared phi I j minus 1 to the n plus minus v delta t divided by 2 delta y. I'm sorry, it should be a delta y here. but usually we assume delta x, delta y are the same, plus k delta t divided by delta y squared times phi I j plus 1 to the n, okay? And then plus minus 2k delta t divided by delta x squared minus 2k delta t divided by delta y squared plus 1 phi I comma j n plus qij delta t. Right? So it looks scary. It looks really intimidating, but you know, remember a lot of these formulas here, we're just going to plug it straight into the code, right? And so, you know, I'm giving you kind of this expression here in kind of a general format because, you know, you can just basically just plug all of these into code. Because basically all of these variables here, all the convection velocities and the time steps and the grid sizing, all of them will just be kind of code variables. All right, question. So there's a left and right and top and bottom neighbor for every direction plus essential. Yes, exactly. Yeah, that was actually going to be my next point too. And so if it makes it easier for you guys, you can kind of, you know, replace each of these I and J's things with, you know, whether they're the left neighbor, the right neighbor, top or bottom. And so instead of I minus 1 comma J, this is basically the same thing as the left neighbor. Right? And so instead of I plus 1 comma J, I plus 1 is the right neighbor. Ij minus 1, that's the same thing as the bottom neighbor. And then Ij plus 1, this is the same as the top neighbor. Okay. And then I comma j, of course, is me. Okay. Okay. Right. And so the name of the game, or basically what we're going to do in the code, is that, you know, everything on the right side of this equation here, they're going to be coefficients in a matrix. Okay. And so, you know, the first thing that we're going to do is we're going to basically form this matrix, you know, of all these coefficients, and then use those to advance forward in time. Mm-hmm. All right. Any questions on this before we jump into the example? Okay. All right. So let me go ahead and describe the example that we're going to do, and then we'll do a little bit here, and then we'll jump straight into the code so you can kind of see it implemented. Okay. All right. And so in this example, we're going to do a 2D problem, and so we're going to work with our usual square domain. Okay. And then all around the square domain, let's say that we just have Dirichlet boundary conditions just for simplicity. Right. And so let's say that we have 30 grid points in each direction. And so this is obviously, you know, way too big for us to solve by hand. Okay. And then the equation that we want to solve is the following. So we have d phi dt plus 50 d phi dx plus d phi dy is equal to 3 d squared phi dx squared plus d squared phi dy squared. And then let's say that we have no source for now. And so, you know, we'll ignore the source term. Okay. And then we want to march this system forward in time using the following parameters. And so let's say we have delta t is equal to 0.0001. Okay. And then the number of time steps that we want to move forward with is going to be 250. Okay. And so we want to march this forward basically 250 steps. Okay. All right. And so if we take, and so basically, you know, we're going to take this equation and start plugging stuff into this kind of massive equation here, right? And so we have, everything here. So we have all our convection velocities, we have our diffusion coefficient, we have delta T, delta X, and delta Y, right? And so eventually, what we want to, what we're going to get is something that looks like this. And so we're going to get an expression for phi I comma j at n plus 1, okay? This is going to be equal to A times phi I comma j at n plus b. Because remember, when we're doing explicit Euler, what we get is not a system of equations, but we get something where we just do basically just matrix vector multiplication. Okay, and so this A right here, this A is going to be our matrix of coefficients. Okay, this phi I comma j at n. This is the value of our solution at the current time step. Right? And so remember, this is always known, right? So anything that's our phi evaluated at n is something that we know already, okay? And this b right here, this b is, you can kind of think of it as everything else. And so I like to call this typically the forcing vector, but it's going to contain things like, it's going to contain terms like from the source term or from the boundary conditions, okay? And so this is kind of like everyone else that's not multiplied by phi. Okay, question? Yes, yeah, NT is the number of time step. Yeah, so the source can be there in general, and I think I actually have it in here, like the slot where you would put the source term. But for this problem, I just so that the results are a little bit easier to interpret, I left the source out. But I'll show you in the example code where you would put the source term if you have it. Mm-hmm. All right, let's see. Okay, so any final questions before we jump into MATLAB? Okay, so let me go ahead and switch to my laptop screen. Okay. Okay. All right, and so if you want to follow along, I did post this code onto Titanium, or God, I went back a year. I did post this code onto Canvas, so you can follow along. And so if you want to follow along, you can go to our class page right here. And then what I'm working on right here is the unsteady 2D diffection diffusion with explicit Euler. Okay, but it's fully worked out, and so there's nothing for you to implement. That's just if you want to follow along. Okay, and so let's come up to the top right here, and then let's go kind of section by section, the way that we usually kind of talk about these codes. Right? All right, so first we have section 1, and so section 1, just like always, for all our codes, we use these to define our variables. Right? And so here I basically, listed out all the variables I'm going to use with a small description of what they do. And so first we have Lx and Ly, and so these are the length of the domain in the x and the y directions, so pretty straightforward. Then we have Nx and Ny, and so these are the number of grid points in the x and y directions, so again, pretty standard. And then we compute the total number of nodes, which is just the product of those two, and also the grid spacing. Right? And so dx and dy here are just going to be the same as delta x and delta y. NT, yes. NT should be 250, thank you. Okay. Okay. Next we have, so this is a bad habit of mine because I think about fluids a lot. Even when I'm sleeping, I think about fluids. And so this whenever you see visc in the code, what I mean is diffusion. Okay. Right. And so this visc is always going to be the diffusion coefficient. But just because it's going to break my code, I'm going to turn this back into visc. Yes, I have a lot of classes that are like fluids, and so my mind is on fluids a lot. And so, you know, I do make that mistake in some of the code, and I didn't realize it until I posted it just like 2 minutes before class, and it was too late to change it. But when you see visc in my code, what I mean is the diffusion coefficient. Yeah. Okay, and so there's our diffusion coefficient. And then next we have our x velocity, and so this is our u in the equation, and then our y velocity, which is v. Okay. And so, you know, from our problem, we saw that our x velocity was 50, our y velocity is 1. Here we have our time step size, which is, you know, 0.001, and then nt, which is 250. Okay. All right. And so the next thing we need to create matrices to hold our coefficients. And so just like I showed you right before I switched here, I created a matrix A for the for the coefficients that we're going to plug in from the explicit Euler, and then B is going to contain basically everything else for the boundary conditions and our source term, which is non-existent. Okay, and so, you know, as the class goes on, you'll see that this section 1 will grow, you know, in every unit that we do, just because we have more things to take into account. And so, you know, relative to what we were doing before, you know, now we have, you know, variables for our time marching scheme. So that's dt and nt, but everything else should be relatively the same. Okay, and so the next part of this code here is section 2. And in section 2, we're basically going to be defining all the coefficients that are in this matrix A. Okay. And so basically, we're going to be taking this formula that we wrote down and basically, you know, writing out the coefficients for the left neighbor, the right neighbor, bottom, top, you know, me, and also the source. Okay. Okay. And so you come into the loop and you first see that, you know, the loop only goes over the interior nodes, right? So remember, we use this convention of 2 to n minus 1 when we only want to loop over the interior nodes. Okay. And so, you know, because normally if you wanted to visit every node, you would do 4 I is equal to 1 to nx, right? But that would also include the boundary nodes. And so we don't want that here. We only want these for the interior ones, because we know for the boundary nodes, we're going to apply the boundary conditions, okay? And so that's why our loop only goes from 2 to n minus 1. Okay? All right, and so the next thing that we do for 2D problems is we obtain the ID numbers for all the nodes, right? And so we have an equation for my ID, right? And so this is the how you get basically the numerical ID from the I and j coordinates, right? So you do j minus 1 times nx plus I, and you have all the sames for you know, all the adjustments that you make for the left ID, right ID, up ID, and down ID, right? And so you can see here for the left, we have I minus 1. Top, we have I plus 1. Right, we have I plus 1. Top, we have j plus 1. And down, we have j minus 1. Okay. All right. And so here's where you start to basically plug in all of these guys. So remember, you know how intimidating these guys looked, but you know, all you have to basically do is just transcribe this equation into your code kind of exactly as it's written. Okay. All right. So first we have the left neighbor, and so for the left neighbor we have A at my ID comma left ID, right? And so this is going to be the row for, you know, this node, but in the column for the left neighbor, right? Because that's what's going to define this equation. And what we have is x velocity, which is u, times dt, which is delta t, divided by 2 times dx. Okay? And then we have the same thing for the diffusion term. And so we have diffusion constant times dt divided by delta x squared, which is dx dx. Okay? And then we have the same, and then we basically just do the same thing for all the other ones, right? Because at this point, remember, we're just defining the matrix that's going to be on this side of the equation, right? And so basically all these coefficients, we're just going to just directly transcribe it to code in the correct spot. Okay. All right. And then this particular problem doesn't have a source term, but if you did have a source term, this is where you would do it. And remember, the source term always occurs. The source term doesn't multiply by phi, right? Right. And so if you can see, you know, all these terms in parentheses, they're all multiplied by a phi term, right? But the source term is not. And so the source term is going to exist in this B vector right here. Okay. So separate from this. And so that's why, you know, for a source term, this is what you would do. Okay. But in this particular problem, I said that there's no source. And so I'm just going to multiply this by 0 just to knock it out. But if you did have this source term, say like 3xy, this is how you would do it. And so the first thing you would do is you would compute the x coordinate, and then you would compute the y coordinate, right? And so you would do those kind of in the same way that we've always done. And so you would take the I and j, and you multiply by the grid spacing, and then your source term would just be just whatever your source term happens to be. And so in this case, in the original version of this problem, I had 3 times x times y. And so we have 3 times x times y, and then you have to add the delta t in there for the explicit whatever. Yeah. Mm-hmm. Right. Question. So would it be easier to define all your variables outside the loop and then just reference them inside the loop? Yeah, no, yeah, that would definitely be helpful. But the reason I did it this way is just kind of more for demonstration purposes. Yeah, but you can definitely define these outside the loop. And so, because right now, every time you run this loop, you're basically doing all this multiplication, division, and when you do this, hundreds, thousands of times, that tends to add up. And so, since in this problem, nothing's really changing, what you can do is you can do, I guess we'll do Vx, right? I guess that's what we want to say. So Vx would be like this times dt divided by dx times dx. And then instead of, writing this whole thing out, you would just reference Vx. But I kept it like this just so you can kind of explicitly see that I'm basically just transcribing these equations into the matrix. Yeah. Mm-hmm. Yeah, but that's definitely kind of a smart way to handle that. All right, any questions on this loop here? Okay. All right, and so now that we've done all the interior nodes, the next thing is to do our boundary conditions, right? And so our boundary conditions are, are relatively simple here, okay? But we have to do an extra step. And so, usually for the boundary conditions, all we have to do is just set, the B vector for our boundary conditions, right? But here we have to do an additional step because, we're time marching, right? And so we have to make sure that our current solution satisfies our boundary condition as well. Right? And so this line right here, this additional line of sol cur at my ID is equal to 50. This ensures initial condition satisfies boundary condition. Okay. Because if you notice, before we jumped into these boundary condition loops, I created this new variable here called sol cur. Remember, whenever you see sol cur, this is basically the solution at time step n, okay? Which, as we know, has to be known, okay? And so that's why we call it the current solution, because it's something that's known. And so basically these additional lines right here basically just ensures that the boundary conditions are satisfied in our initial conditions, okay? All right. But for this problem, it's relatively simple since we have Dirichlet conditions all around. And so you can see, as we loop over the top boundary, we set the, the solution equal to 50. When we loop over the left boundary, the solution is equal to, where's the left boundary? Left boundary is up here. Left boundary is equal to 50, top boundary is equal to 50, right boundary is equal to 25, and bottom boundary is also equal to 25, okay? Okay. And so now that we've done that, now our B vector and our current solution is set. Now we're ready to plot, okay? All right, and so here we have our time marching loop. And, I will say that, everything that I'm highlighting here in blue, all of this is just for plotting. And so the only thing that you need for time marching, now that we've set up this A and B, is just these lines, these 2 lines of code, okay? All right. Any questions before we start talking about the time marching? Okay. All right. So let's talk about the time marching. And so you can see the first thing that I do is I create a variable for sol next. And for sol next, this is simply the solution at time step n plus 1, okay? Which we know is going to be our unknown. Okay? And so this is what we're basically going to be solving for in every time step, okay? Okay. All right. And then this end plot right here, this end plot is just it's just an additional counter variable. So it's just to basically plot things on separate figures, but it's not necessary for the solution, but it'll help with the plotting. You'll see what it does in a second. Okay, and so now let's go into the actual time marching. Okay, and so just like we saw with our 1D problems, whenever you're doing a time marching scheme, you have to have some loop that loops over time. And so whenever you you should look for this loop every time you do an unsteady problem. So this loop iterates over time. And so what we have here is we have 4t step is equal to 1 to nt. Okay. And so basically what this is saying is we're going to loop over nt time steps, where for this problem nt is going to be equal to 250. And so this loop is going to repeat 250 times. Okay. All right. And then in order to compute the next time step, we're just going to implement this equation right here, right? And so because we've established our matrix A, because our matrix A has all of our coefficients, we've established our matrix B, and we also have our current solution, which is which we kind of already started modifying a little bit. And so to get the solution at the next time step, all we have to do is we have to do sol next is equal to A times sol cur plus B, which is basically the direct implementation of this. Okay. And so this solves for solution at n plus 1. Okay. All right. But you not only need to do that, you need to do this next step too, because this next step, what it does, which is very important, this updates the current solution. Okay. Because at this point, your loop is basically going to get ready for the next iteration. And so for the next iteration, what the solution basically expects is that your sol cur here, or your current solution, is going to be updated from by what you solved for in the previous step. Okay. And so what we do is we basically use MATLAB's assignment operator here to do sol current is equal to sol next. And so what this does is that now that we've solved for the solution at n plus 1, now our current solution will be what we just solved. And then now we're going to get ready to solve for the solution at the next time step. Okay. Okay. Any questions on that so far? Okay. All right. And so this last part of the code right here, this is just for plotting. Okay. And so what you'll see, and this will become a lot more apparent, in lecture notes 8, is that now that we're doing unsteady problems and things are changing with time, we're basically going to be solving for the solution, we're basically going to be solving for 250 solutions. And you can think of each solution as like a frame in like a video, right? And so oftentimes it's a little bit too much to print every single frame for your solution, because you can imagine 250 figures pop up and it might crash my computer. Not even joking on that. So 250 is a lot. And so basically what I do here is I only plot it every 10 time steps. And so that's kind of what this line of code does. And then I've included, here's the code that I've included in all your 2D codes to help you plot it. Okay, so you don't have to worry about that. And then here I've plotted the solution here. Okay. All right, so the question is, how does this differ from previous 2D convection diffusion? Previously, we did A/B or a linear solve. Yeah, no, that's a good question. Because previously, what we did was we kind of solved for the steady state solution. And so time wasn't a factor. But now that time is a factor, and we can choose between explicit Euler and implicit, the explicit method has this kind of matrix multiplication solution. But it's a good observation, because actually, if you kind of look at the problem that we have here, this example problem, you'll see that it's actually a steady problem because nothing actually changes with time. Besides the fact that we're starting out with an initial condition that's 0, nothing in this problem is actually changing with time. So our convection velocities are not changing with time. Our diffusion is not changing with time. Our boundary conditions aren't changing with time. And so what we'll do in the next set of lecture notes is we'll actually do situations that actually do change with time. And so you'll see how that's implemented. But right now we're kind of doing a time marching implementation of a steady problem. But whenever you do time marching, you're only going to do a linear solve or linalg or backslash, when you do implicit Euler. And so when you do explicit Euler, you just do this matrix multiplication thing right here. And so it always ends up with the fact that, explicit methods are usually a lot cheaper and a lot more easy to implement. But remember, the danger of explicit Euler is that you might end up with unsteady solutions, okay, if your time step size is small enough. Okay, so let me go ahead and run this code, and we can go ahead and see what it looks like. And you'll see 25 figures pop up. And so let's pray for my computer that it doesn't crash running Zoom and MATLAB at the same time. Okay, and so you can see here that there's the 25 figures, and the Zoom bar is like right on top here. And so you can imagine basically, each of these windows are a different frame in a video. Okay, and so here's the first frame, and so this is the initial solution. Okay, then we go to the second frame, then the third frame, then the fourth frame, then the fifth frame, 6, 7, 8, 9, oh, this is 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay? And so you can see that the solution is evolving with time, because we started out with a solution that didn't satisfy our equations, and eventually over time then it does. Yeah. I have a laptop, so it's a gaming laptop. So I mean, I didn't think that it would crash, but you never know. You never know sometimes. Yeah. All right. And so that's basically the MATLAB implementation of a 2D convection diffusion unsteady with explicit Euler. Yeah. Mm-hmm. All right, question. So does MATLAB have a way to animate different figures? Yes, it does. And so we'll see that in the next set of lecture notes. And so basically the next code example that I give you, I'll show you the commands to actually make a video within MATLAB. Yeah, but that's coming next. Mm-hmm. But for this example, I just wanted to show you how to implement, the whole thing with the A matrix and the B, and how to actually do the time margin. Yeah. Just down one more round. I'll keep that in mind. All right. So any final questions on this example before we go back to the notes? Right. Yeah. So what you guys just saw was basically, initially, what we're starting with. I kind of did gloss over this point, but eventually, initially, what we started with is we initially started with a solution of all zeros, right? So let me run it one more time. And we'll see my computer spaz out again, okay? And so if we look at this initial frame right here, you can see that the majority of this plot here is 0, right? And that's because we started with 0 initial conditions, right? And so the only exception to this are the nodes that are on the boundary, right? And so we start out with a solution that's predominantly 0, but our boundaries are non-zero. And then eventually, over time, what it does is that it basically comes to an equilibrium solution. Okay. And so if you could kind of, think of this as like a flip book and then kind of flip through it really fast, that's why we're, that's why we're doing this. Question. So why, if we did NT is equal to 250, why did we only get 25 figures? And so that was kind of the small adjustment that I was telling you right here. And so basically I made it so that I only plotted every 10 time steps. Yeah. Yeah, because if I did 250 figures, I think my computer would probably cry. It probably wouldn't crash. I have more faith in my computer than that. But yeah. But so this is probably only a problem for this one, because in the next set of lecture notes, I'll show you how to actually make a video. Yeah. Yeah. So for a video, you don't have to worry about that because you just produce basically just one MP4 file where you can view the solutions. Yeah. And actually, if you want to see something cool, I can show you last year's projects now that I have you here. And so this is basically what they did last year. So let me show you the most fine one. Right. And so this is what they did in last year's project. So they basically just simulated a washing machine, basically. Yeah. And so this video here was created in MATLAB. Yeah. So your guys' project is going to be different than this, but you know, it's going to use all the same methods. Yeah. All right, question. So is this like something that's being heated? Yes. Yeah. That's exactly a good analogy. So you can almost think of it as like a square piece of metal, and you're kind of heating it from the outside. And so it's basically starting cold, and then eventually that heat is going to creep into the middle of that that domain. Mm-hmm. All right. All right, so that was explicit Euler, and so I'll give you the equation for implicit Euler next, but I'll save the implementation details for the next set of lecture notes, because you know the next set of lecture notes will show you how to implement implicit. And actually, you know, the implementation for implicit Euler it is actually quite different from explicit, and so you know, just keep that in mind. But you know, just kind of you know, keep an eye out for it once we get to that part of the. I think it's going to be the very last example that we do in the next set of lecture notes. Okay. All right. And so this was explicit Euler. And now let's do implicit Euler. For 2D unsteady convection diffusion. Okay. All right. And so, you know, we're going to derive these equations in a very similar way. But remember, for implicit Euler, what we do is that we take all of our spatial derivative terms and we evaluate them at n plus 1. Okay. Okay. And so the starting point is going to be the exact same equation, right? And so we're going to have d phi dt plus u d phi dx plus v d phi dy is equal to k d squared phi dx squared plus d squared phi dy squared plus q of xy. And then just like we did before, we're going to replace all these derivatives with finite difference. And then we end up with the following. Okay? And so first we have our time derivative term. And so this is going to be phi I comma j at n plus 1 minus phi I comma j at n divided by delta t. Okay. Next we have the x velocity term. And so this is going to be u phi I plus 1 comma j minus phi I minus 1 comma j divided by 2 delta x. Okay. But since we're doing implicit Euler here, you know, what we're going to do is we're going to evaluate these phi terms at n plus 1. Okay. Because previously what we did was we evaluated them at n for explicit Euler, but for implicit Euler we do it at n plus 1. Right. Next we have the y. So this is phi I j plus 1 minus phi I j minus 1, okay, all over 2 delta y. Okay. Where again, we're going to evaluate this at n plus 1, n plus 1. Okay. And this is equal to, same thing on the right. Okay. And so first we have our x diffusion term. So our x diffusion term is going to be k phi I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j all over delta x squared. Okay. And all these guys evaluated at n plus 1. And we have the y derivative. So we have phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1 all divided by delta y squared. All these guys evaluated at n plus 1. And of course, we have our source term as well, which I can squeeze just in the bottom here. Okay. And our source term, you know, it doesn't have any fees to it, and so we don't have to worry about that. Okay. All right. And so just like we did for explicit Euler, what we're going to do is we're going to take all the phi terms at n plus 1, put them on the left side of the equation, and all the terms with phi n, we're going to put those on the right. But because, you know, we evaluated these spatial terms at n plus 1, we're going to end up with a much different looking equation than what we did before. That color's too white. All right, let me see. What color haven't I used yet? I haven't used light blue. There we go. It's a little better. All right. And so, you know, I'm you know, just because we're a little bit short on time, I do want to get to the next set of lecture notes. I'm just going to give you the final result, but you can kind of, you know, work through the algebra yourself just to make sure that, you know, all of these guys are correct. All right. Any questions on this? Okay. All right. And so just to kind of summarize, you know, the steps that we're going to do. So this is everything at n plus 1, right? And so all the phi terms at n plus 1, we're going to shove it to the left side. And everything at n, we're going to shove it to the right, plus the source term. So the source, we're going to keep it on the right. That's it. Okay. All right. And so we end up, and so now we end up with a system that's much more heavy on the left-hand side than it was on the right. Okay. Okay. And so what we get is the following. So we have minus u delta t divided by 2 delta x plus k, or minus, sorry, k delta t over delta x squared. This is phi I minus 1 comma j n plus 1. Okay. And so that's the left neighbor term plus u delta t divided by 2 delta x minus k delta t over delta x squared times phi I plus 1 comma j at n plus 1 plus minus v delta t divided by delta y squared, or 2 delta y, minus k delta t divided by delta y squared phi I j minus 1 n plus 1, okay, plus v delta t divided by 2 delta y minus k delta t divided by delta y squared phi I j plus 1 at n plus 1, okay, plus 1 plus 2k delta t divided by delta x squared plus 2k delta t by delta y squared phi I comma j n plus 1. This is equal to phi I comma j at n plus Qij delta t. And so this right here is our 2D unsteady convection diffusion with implicit Euler. Okay. And so you can see now we're much more heavy on the left-hand side. All right. And so just like we saw, in our 1D implicit Euler solutions, basically what this is going to give us is a linear system of equations. Okay. And because if we extract all the coefficients here, which is essentially what we basically have a lot of coefficients for a lot of linear equations, we end up with a system that looks like this. Okay. And so on the left-hand side, we have a coefficient matrix A multiplied by phi ij at n plus 1. And this is equal to phi I, comma j at n plus q ij delta t. Okay. And so if we kind of summarize this this sum here, because everything, remember, on the right-hand side is known, right? And so if we summarize this this right-hand side as like some vector b, then we can use this and solve for phi I, j, n plus 1. Okay. All right. And so there's kind of one last thing I want to show you on the next page, and then we'll move on to actual time-dependent problems. But this was kind of a lot to write, so I'll give you guys kind of a minute to write this down. And so while people are catching up, are there any questions on this? It's a lot, yes. It's a lot of writing. Okay. Am I a laminar flow guy or a turbulent flow guy? I mean, most of the work I do is laminar flow, actually. So and so I work with blood flow a lot, and so blood flow is mostly laminar, believe it or not, which is actually very unique. And so I do work with laminar flow a lot more than I do with turbulent flow. But I'm aware of what turbulent flow is, and I have nothing personal against it. I just don't work with it. Okay. And so now that we have this, now we can go ahead and show you what's up with this. Because remember, the ultimate goal for every time marching scheme is that is to solve for phi ij at n plus 1. Would it logically make sense for blood to be laminar? So yeah, I mean, because your blood vessels are typically really small, that ends up, the Reynolds number ends up being, really small. But, there are some cases where you can get turbulent flow there. Oh yeah, yeah. So Ronald was in a class I taught last year for advanced viscous flow, and so there we covered turbulence there. And the funny thing about turbulence is that, relatively speaking, we know very little about it. And so anyone that tells you that they understand turbulence, they're just flat out lying to you, because it's because we don't understand turbulence. Yeah. All right, and so let's go ahead and finish this up. Okay. And so if you remember from our explicit code, there was a point in the code where we had something look like this. We had sol next is equal to A times sol cur plus B, right? And so this is for explicit Euler, because remember, for explicit, we do just matrix multiplication. Okay. But for implicit, we're going to replace this side of the equation with a linear solve, right? And so what you'll see instead is that you'll have sol next is equal to A backslash, and then everything on the right. And so on the right, you'll have sol cur plus B, whatever your boundary conditions and source terms are. Okay. And so this is kind of the primary difference between explicit and implicit. And so, your coefficients are also different here. And so you can't just take the code that we just wrote and replace that one line of code here, because your A matrix is going to have different coefficients, because we're working on kind of the other side. But the primary cost difference is basically in here. And so instead of doing matrix multiplication, you're doing a linear solve, which is much, much, much more expensive. And so going implicit is a big decision, because you're going to add a lot of cost to your simulation. But what you get from it is you get a solution that's always going to be stable, right? And a lot of times that's really valuable, especially in light of what we're going to be talking about next, which is situations that actually do change with time. And so what can happen sometimes that there might be just a brief instant in your time-dependent problem where you go unstable. And just for that brief instant, that brief instant might mess everything up if you do an explicit solver. And so, for those problems where you have kind of a really unsteady velocity, an implicit solve might be the better option just to make sure that it's stable. Yeah. Oh, I'm actually not. I should sub to that and see and check that out. All right. Any final questions on lecture note 7 before we go on to actual unsteady problems? Yeah, I'll check it out after today. Maybe as I'm eating dinner. Yeah. Okay, so let's move on. And so this is kind of part 2 of our time marching notes. And these are basically time marching problems where our properties or boundary conditions actually change with time. Okay. All right. And so up to this point, we've covered time marching schemes, but we haven't actually covered any situations that change with time, right? And so how do I know this? And so, and the reason I know this is because if you look at all the examples that we've done up to this point, there's been no t, right? Right. And so if you look at our past example, you can see that we have a convection velocity that's constant, we have boundary conditions that are constant, we have diffusion constants that's constant, right? And so nothing has changed with time yet, right? And so what we've looked at are situations that are basically coming up to steady state. but we're kind of limiting ourselves here because, in reality, there are a lot of situations where things change with time, right? And so, one example that that I can tell you, based on, the final project from last year, that had basically a convection velocity that changed with time. And so because our convection velocity was changing with time, we were able to get that kind of psychedelic, thing that was going on with the washing machine. Okay. And just in general in engineering, there's a lot of situations where, we have to change with time. Right? And so some examples that, that you can use these for are, the temperature of a material undergoing annealing. And if you're unfamiliar with what annealing is, it's basically repeated cycles of heating and cooling, right? And so you'll heat up a material, you'll cool it, you'll heat it up, and you'll cool it. And over time, this improves the material strength, the material properties of the material, right? And so with that, you're constantly applying, heating, and then you're letting it cool, you're letting it heat, you're letting it cool, and so things are changing with time there. Okay. What is this? Okay, it's not T factorial. Yeah. that is another that's another example that Juan described there. It's a little bit inappropriate, and so I'm already kind of on the hot seat a little bit with the dean, so I have to watch a little bit what I say. So I won't say that out loud, but that is a great example of that. Okay, and so kind of a very similar application of that, but not the exact same situation. Whereas you can simulate pollutant transport in the atmosphere with winds and changing with time. Okay. And so, there's a lot of situations that where, we need to introduce time into our equations in order to accurately simulate them, right? Because not everything is going to be, not everything is going to be a steady state problem. Okay. And so, what you'll see is that this is kind of a small kind of addition to what we have been doing, because, we've done kind of the bulk of the work with time marching. And so, most of the time marching is done. Is what you'll see is that we'll just kind of make one small adjustment in order to account for this. we can I'll think about it. All right, any questions on this before I go over that kind of one small adjustment that we'll do? Okay. All right, and so the small adjustment that we'll do is the following. And so in order to have things change with time, we need to keep and maintain a time variable. Okay. Right, and so basically, what you'll see in our code is that, we're going to define a variable called t, and we're going to initialize it to 0. Okay? And then each time that we iterate in time, we're going to increment this time variable by delta t. And so hopefully, after we do this, the time step size delta t is going to have a lot more meaning now, right? And so in every time loop, basically what we're going to have is t is equal to t plus dt. Okay. All right. And so basically, we're basically now keeping track of what time our solutions are taking place, right? Because remember the analogy that I talked about before, where you can think of our solution to an unsteady problem as like a video, right? Where we're basically simulating each frame of that video. And then now that we're bringing this t variable in here, now we can basically say which time each frame takes place. Okay. And so basically, time is going to progress basically linearly, and then every time step, basically, we're going to have a different frame. Okay. All right. Any questions on this? Okay. All right. And so kind of the way you can kind of visualize it is like this. And so we kind of have our time axis like this, right? And so basically, we're going to be advancing from t is equal to 0 to to whatever. And so this will be like t1. This will be like t2, t3. Right. And so at t1 right here, we're going to start at 0. Then in between t1 and t2, we basically say that delta t has passed. Right? Okay.
Hey, Professor, sorry, can you go back to the previous page?
Sure. Mm-hmm.
Thank you. We're good. Thank you.
Cool. Thanks. Right. And so this, we've already kind of been doing this. And so we've kind of already been saying that each frame is kind of been separated by delta t. The only difference now is that we're actually going to use this t in our equations. All right, so let me show you just a quick example. I don't think I'll have time to go over in detail, but I'll at least be able to show you the video. Let's do an example with basically a vibrating string. Okay? And so this is actually the same 1D diffusion, unsteady diffusion problem we did before. I'm just going to make one small adjustment to that so that the boundary conditions are changing with time. All right, and so just to kind of refresh your memory, this is the example that we did. And so we had partial phi partial t is equal to 3 partial squared phi partial x squared. Okay, and so you can see here that we have unsteady diffusion. Okay, and so here we have our boundary conditions. And so first thing we have is phi is x equal to 0. Okay. So I think what we had before was that this was just simply a constant, but now I'm going to change this to something that changes with time. Okay. Right. And so we have a Dirichlet boundary condition on the left side, but now that left side is going to be cosine of pi t. And on the right side, we're going to have just a constant flux boundary condition or Neumann boundary condition of 2. In our initial condition, we'll say that we start everything out at 0, just for simplicity. Okay. And so for this problem, I think just to give you a different look, I told you to implement this with implicit Euler. Okay. And so, nothing's really going to change. And so, we're still going to apply the same, time marching scheme as we did before. The only difference is now that our Dirichlet boundary condition is going to change with time. And so you'll see time enter as a variable into that expression. Okay. And so let me give you some more parameters here. So let's say that delta t, since we're doing implicit, we can be a little bit more aggressive with dt. And so we can say our delta t is going to be 0.1. And our delta x here is going to be 0.25. And we want to simulate this for 5 grid points in space. Okay. Okay. And so I have 1 more minute, and so I think we'll save the bulk of this of the math for this problem for next time. But I do want to show you what the results look like. Okay. And so any questions on this before I jump back to my laptop screen? Okay. So let me jump to my laptop screen really quick, just so you can see the solution. Okay. And so this is another code that I posted onto Canvas. And so this is fully worked out. And so you don't have to add anything to this. And we'll go over the details of this next time. But what you can see here is that, I've implemented basically this time dependent boundary condition. So we have cosine of pi t right here. Okay. And I've also included these lines of code here to basically make the video. And so we'll go over this next time too. But if you run it, you can basically see the string is basically vibrating just like that. Okay. So I'll run it one more time. Okay. And you can see the string kind of rotating up, vibrating up and down. Okay. And so you can kind of see on the left-hand side here that the value for this Dirichlet boundary condition is oscillating between 1 and -1, just like a cosine wave does. All right. Any final questions on this before we sign off for today? Oh yeah, that's for 442. So that's for another class. Yep. My VMR files. What is VMR? Oh, oh yeah, you can. Yeah, so those are for the final. Actually, yeah, Simon, I keep forgetting. I need to check base on you with the project, but we can kind of discuss that in private. But yeah, you can see a few more of those. Let me see. Where is it? 442 share. Yep. So this is for the final project for EGME 442, and so they're going to be running a CFD simulation on blood vessels actually. Mm-hmm. Yeah. So this is what they're trying to get, but whether the students get this will be we'll see. I use for these I use a different program called ParaView. So that's my favorite kind of 3D visualization software. Yeah. All right, so we're out of time. So I'll be here to hang out if you want to see more of these pics, but there's nothing more about computational heat transfer for today. So thank you guys for tuning in today as usual. And so on Wednesday we'll pick this up and we'll talk about we'll discuss this vibrating string example in detail. and we'll do a 2D example too. So thank you guys for tuning in. Have a good evening, and I'll see you guys on Wednesday.
Hey, Professor, quick question. The video or the lecture that you did last Monday, I can't access it through the Canvas on the week. Is it already uploaded, or am I not looking at the right?
Let me check. I might have forgotten to upload it because it's because we had the exam last week. Let me see. I did not upload it, so let me do that right now. Actually,
Awesome.
Thanks for reminding me.
Thank you, Professor.
Yeah.
All right. Take care.
You too. Oops. That's part 2. Oh, your Zoom is glitched. You can you'll be kicked out once I close the room.
Professor?
Yep.
Could you go back to the first example of lecture 8 notes? I didn't.
Yes.
Thank you.
Stop this. Come back here. Yeah, we'll go over this a lot more in detail on Wednesday. You're talking about the vibrating string example. Yeah, so far I've basically just written down the problem, but we'll go over this in kind of detail next time about how you get the coefficients and how you plug stuff in for this.
Okay, thank you.
Do I feel like all these online lectures are preparing me to be a streamer? I don't think I'm entertaining enough to be a streamer. I do have a couple friends that stream, and so actually I take a lot of inspiration from them for my virtual lectures. But I think it's kind of a one-way street, so I don't think I can stream. Plus, I play mostly boring games, and so I play a lot of just like story-driven, JRPGs, and so those aren't the most exciting to watch. My friends tell me that all the time. Oh man, kind of looks like you're stuck. I just don't really react or do anything when I play games. I'll just sit there and I play, and so yeah. I have heard of it. Yes. I played about halfway through, but it came out during a time when I was kind of really busy in my life, and so I didn't end up finishing it. But I do have it, and I do want to finish it someday. Little Nightmares 2. Oh, interesting. Do I consider SIO a trash anime or decent anime? I mean, I thought the first season was really, really good. I mean, and of course, the opening songs with Lisa are great. I didn't hate the second part with the little sister as much as most people did, but it just didn't. I just wasn't really interested in watching future seasons beyond that. But I thought it was fine. Let me stop recording before.